Welcome to my Acoustic Fluid Level Shots e-course. My name is Sean Dawsey. I am the creator of this course, and I will be your instructor for this course, hanging out with you down here in the bottom of the slide. So if you want to tell anybody about this course, the easiest thing to do is to tell them to go to fluidlevelshots.com. It will link over to this course hosting platform. But let's go ahead and jump in. So in this course, I'm going to open up to you the whole library of knowledge when it comes to fluid level shots. We're going to look at how do you take a fluid level shot? What is the theory of it? How do we interpret the acoustic trace? We'll look at difficult to interpret acoustic traces. How do we disentangle all the different kicks that we're looking at? How do we get a good reflection off a well where it's not easy to see the fluid level kick? What are some of the ways to enhance the signal to noise ratio we're seeing in the acoustic trace? How do you calculate the bottom hole pressures? How is the software working? What are some of the assumptions that are going in the software? Some of the correlations that have a big influence on the output for the calculated amount of fluid that is down there above the pump, and also the bottom hole pressures. We're going to go into all of that. And if you want to know what topics we're going to cover and in what order, you can look at the detailed outline that lays out each topic sequentially as we go through the different sections. And when you look at that, you might say, wow, this is a lot of information. And it is. But as the great Thomas Paine once said, the harder the conflict, the more glorious the triumph. And I promise you, at the end of this course, if you pay attention, take notes, think about it, play along with me, actually have the Echometer TAM software, look at some of the example files that I give you kind of as practice. Try to do those before I give you the answer. If you do all of that, you'll become an expert when it comes to fluid level shots by the end of this class. So let me tell you a little bit about myself so you know where I come from. But I graduated from Texas A&M in 2009. And Texas A&M is just outside of Houston, Texas, but I graduated with a petroleum engineering degree, and then I moved out west to Midland, Texas, and I worked for a smaller operator, Discovery Operating, as a general production/operations engineer for the first 3 years, and then I was the production manager for the last 2 years. So Discovery Operating has they had about 250, maybe 300 wells that were scattered across the Permian Basin when I was working there. And when I was younger, I just wanted to apply myself. So I've never been the smartest person, but I've always been the hardest working. And so when I was a young engineer, was not married, I didn't have kids, I started diving into rod pumping systems, primarily because that was the main form of artificial lift that we had with the operator. And so I studied everything I could get my hands on. I read all the literature on it. And I remember at one point, I was sitting in the library on a Saturday in the downtown library. And as you can imagine, in Midland, we have a great petroleum section there. But I was reading more literature on rod pumping, and I realized, I already know all this stuff. Why am I still sitting here looking at the theoretical information on rod pumping systems when I work for an oil company and I can make the field my laboratory? I need to start going out to the wells and actually playing with them. And that's where I tried to marry the theory with the practice. So I talked my company into buying a set of the Echometer fluid level gun and dynamometer system, and I started running around and playing around with the wells. I learned a lot, and by getting that information back from the wells, I was able to make quite a few changes when it came to improving our downhole gas separation, but also in trying to minimize our overall failure rates. So the owners of the company saw that my interest in this, and they made me the production manager for the last 2 years that I was there. Now in 2014, I became a professional petroleum engineer, which means that I just certified my competency as a petroleum engineer. I can give expert testimony in litigation, that sort of thing. More importantly, though, in 2014, I started my company, Downhole Diagnostic. So if you've ever seen my logo or my company name, anything you've seen from my company has come from me. I'm a one-man show. I've been a one-man show, and I've been doing this for over a decade now. But primarily what I do at Downhole Diagnostic is I'm a field hand. I go out to the field. I connect equipment to the wells. I'm taking fluid level shots. I'm doing dynamometer tests. I'm looking at pump off controllers. I might be raising, dropping rod strings, but really trying to help customers understand what's happening in their wells. So what are the downhole conditions? What is the well telling us? And what is the best path forward to optimize the particular POC settings or to optimize the way that we're operating this particular well? So that's primarily what I do. I also do some artificial lift design, and as you can see, I also do some rod pumping related training. So if you look at my company name, Downhole Diagnostic, I picked it specifically because it's quite descriptive on what my company does, but also I like the etymology of it. So dia means through, and gnostic means wisdom, and there's kind of a connotation with Gnostic which indicates esoteric wisdom, especially if you look back at the religious sect of the Gnostics back in the 1st century. But that's what I try to do. I try to bring esoteric or knowledge that's not as commonly known to my customers. So instead of just getting data and throwing it at them, I try to create a complete narrative with the data that I'm getting from the well and saying this is where the well is at and this is where we should try to take it to best optimize the profitability or the longevity of the runtime for the particular wells. So anyways, that is my background right there. Let's go ahead and jump into the course. So what I'm going to do for the rest of this introduction here is I'm going to do a little housekeeping here at the beginning, and then I'm going to review the sections and I'm going to show you which topics that we're going to cover in which order, just to give you kind of a higher level overview of what's going to be coming up. But before we do that, this is copyright protected, so please do not copy, share, or reproduce this in any form or fashion. I would greatly appreciate it. So the videos in this course, excluding this one, have been lifted out of my masterclass. I have a 50 to 60 hour rod pumping diagnosis and masterclass course, and I worked on that for over 5 years. Of course, I had a job and a family and increasing numbers of kids during that time, but any free time that I had, I invested in that course. So I put a ton of time into it, and I've lifted out the fluid level shot videos for this specific course. But the point of me saying that is that I've invested a ton of time and tried to make this course as high quality as possible, and I think you're going to see that. So please respect my copyright on this course. Now, this course is designed to be computer-based, so the size of the images, the size of the font are designed for you to be sitting at a computer and looking at it. You can try to watch this course on a phone, but it's probably not going to work too well just due to the sizing of everything that you're going to see here on the slide. But it might not be a bad idea if you watch a video and let's say you're interested in something or you want to review it, maybe you can try to stream it as you're bumping down a lease road driving out to some wells. Now, this course is also not designed for you to buy one access pass and then put it on a projector screen for your whole company. Please, again, one access pass per person. I do give bulk discounts if you have multiple people that want to sign up. But again, please support my work. I've invested a ton of time in this class. So here is the section outline for this course. So we're in the introduction right now, and I'm going to give you an overview of these different sections right here. So we've got fluid level shot basics, fluid level shots overtime, and then the final quiz, which is 2 hours. And then notice right here at the end, we have an echometer equipment and software section if needed. So this is after the final quiz because you might not be interested in this and you don't need to take this. This is why I put it after the final quiz. In here, I talk about the differences between the wireless versus wired equipment. And probably more importantly, I go into the 2 different software programs from Echometer. So the old version of the software, TWM, and the newer version of the software. And in this class, we have some example files for the TAM software, which you can play around with, and I highly recommend you do. So if you don't have that software, you can download it free from Echometer's website, and I'll talk more about that. But if you're interested to become better in working with the software, you might take this section next after the introduction and then start off in these next 2 sections, because all the images that you're going to see are coming from the Echometer equipment in this course, and it's a fantastic software program. Also, there's some other examples that they give for free with the software that you can also play around with and try to analyze on your own. But let's go ahead and jump into the second section. So here are the main topics that we're going to discuss. We're going to start off by looking at the components of a fluid level gun. We'll look at the theory on how you take a fluid level shot and what's happening, and I'll show you the steps to safely connect and take a fluid level shot on a well. Then we're going to look at the acoustic trace. So there is a microphone here in the bottom of the gun, and that is what is recording the acoustic trace. All the sound waves that are reflecting back to that microphone are plotted out here on this strip with respect to time and with respect to depth right here. And you're getting sound waves that are reflecting off cross-sectional changes that are occurring downhole. So we have down kicks and up kicks. So we're going to look at acoustic traces, and we're also going to focus on the polarity of kicks and look at lots of different examples to make sure that you're familiar or good at interpreting acoustic traces and the different types of kicks you can get from the various different types of cross-sectional changes. So if you look at here, there's a down kick from a TAC. We've got an up kick here a big one. Here's a little one from a perforation. Here's a big one from a perforation, which would indicate that this perforation right here is more open. It's reflecting back more energy. Then the next topic is going to be the gaseous fluid column and the casing pressure buildup test. So if you take a fluid level shot and you find the fluid level, let's say it's right here in a particular well, if there is gas that's bubbling up through the liquid, this is what we call the gaseous fluid column, and it consists of both liquid and of gas. And what's really important when you after the fluid level shot, you do a casing pressure buildup test, and you see how fast the casing pressure rises. So for example, it's rising at 0.09 psi per minute. Well, that then feeds into a correlation in the echometer system, and the output of that is our model of the well. So if you were to allow all of these gas bubbles to rise up here to be with the rest of the gas column, and the liquid was to then fall, this is what the model of the well looks like. And you can then calculate what the bottom hole pressures are based on the vertical height of these different columns. So we could calculate what our pump intake pressure is and our producing bottom hole pressure. Then after that, we're going to talk about the 3 different methods for calculating the acoustic velocity. So when you take a fluid level shot, bang, we release the energy into the well, and that creates a sound wave that then travels downhole through the gas medium, and it travels back up to surface. Now, in order to calculate the distance to the fluid level, you first have to identify which of these kicks is the fluid level kick. Here it is on this particular trace, but then we need to know how fast the pressure wave is traveling. And the primary way that we calculate the acoustic velocity is based on calibrating to the frequency or the number of tubing collars that we see per second. But you can also use a downhole marker like I'm doing right here. I'm marking this perforation, which I know what this kick is. It's this perforation, and I know what depth it's at. So we can use various different means, and it depends on the situation as to what the best method is for calculating the acoustic velocity. But very important here, most people who are beginners with fluid level shots really do not understand all the different methods and when to apply them in when it's best to apply different methods for calculating the acoustic velocity. So this right here is very important. Then for the rest of this section, we're going to focus on getting good quality data. So we're going to look at background noise that can basically obstruct or create noise here on the acoustic trace that we don't want to see. We'll look at the shot size. How much should you pressure up the gun? We'll also look at wellhead connection. So how are you tying the gun onto the well? How open is it? How many turns are there? That can limit the ability or the clarity of the signal coming back to the microphone. So what we're going to focus on is basically acoustic traces and the theory, the acoustic velocity here, in getting good quality acoustic traces that we can then interpret. Then in section 3, this is where we're going to go overtime on fluid level shots. And we're going to start off with digital filters. You can apply a digital filter to the tubing collars. So for example, here's some tubing collars from 4,200 feet to about 4,600 feet right here. And you can see this is the 11-point divider, and you want to ensure the software is properly on the collars, but it's hard to see if it's actually on the collars. This is in the raw form, but we can put on a high pass filter, and now you can see those collars are accentuated. They stand out better from the general background noise that's coming back to the microphone. Or we could even put on a heavier filter, the bandpass filter, which you have to be a little cautious with this one right here, which really smooths it out. So we'll look at putting filters on collars, and the reason you do this is to calculate the acoustic velocity. You want to verify the software is properly interpreting the collars to calculate how fast that pressure wave is traveling downhole and coming back to the microphone. Now you can also apply filters to the acoustic trace. And the reason you would do this is to try and identify downhole kicks, especially the downhole fluid level. This is a fluid level shot on a well that had a bunch of fluid that was falling from surface downhole. It was essentially kind of raining in the annulus, and that was due to the fact that there was a slipstream that was taking fluid from the tubing to the casing to help carry the continuous chemical downhole, but that slipstream was way too open. And so when I got there, you could hear a lot of fluid going through there. I shut it off, waited a little bit and took a shot, but there's so much fluid falling down, you can't easily pick out the fluid level kick. But it's actually right here. You can see that white space, but it stands out much more if we put the low pass filter on. So we're going to focus on using filters to help us see what we want to see, whether it's tubing collars or downhole kicks like this. And that's going to help us then in the next section. So here we're going to get into troubleshooting features. in looking at very complicated acoustic traces. So if you're familiar with the TAM software, we're going to be in this section right here where you overlay previous shots. You can use a depth reference marker, or you can fold the acoustic trace, and that's going to help us to interpret acoustic traces that look like this. So for example, on this one, what are we looking at? Where is the fluid level kick? We have all sorts of kicks that are going on here. Or what about this one that has a big casing leak higher up in the well? There's a big upkick here that rings up and down. Well, how do I identify where the fluid level kick is if I don't know which of these kicks is the fluid level kick? So we're going to look at more complicated acoustic traces in this section, and I'll show you how to disentangle those and properly interpret the fluid level. Then we'll look at the implosion shots. We'll look at implosion shots with Ecometer's 1500 PSI gun. And if you do not have the Ecometer equipment, almost everything we discuss in this class, the principles of this you can apply to an acoustic trace from any type of fluid level gun. Or an implosion shot, you can probably do the same method with any type of fluid level gun, depending on what the capabilities are in the software. But typically we do an explosion shot. We shoot energy from the gun into the well. An implosion shot is vice versa. You're shooting energy from the well into the gun. And you might do that because maybe you go to a well, you've only got 1,000 PSI of nitrogen, but the well's got 1,100 PSI on it. Well, you can't shoot into the well because the well has more pressure than the gun. So there is a workaround method. This gun is not designed for that, but there is a workaround method in order to do an implosion shot with the 1500 PSI gun, and I will show you the methodology for that. Then we're going to focus on the Ecometer S-curve and the G-flap, or the gas-free liquid above the pump calculation. So remember when we have the gaseous fluid column and then it goes into a correlation, and then the output of that is our model of the well, where we have the gas bubbles rise up, the liquid falls down, we can see how much fluid is above our pump and how much fluid is above our perforations. Well, this is the correlation in the Ecometer software. It's called the S-curve. And we're going to go into detail on this because this curve is absolutely important to the calculated output values. For example, how much fluid's above the pump? What are the bottom hole pressures? And we're going to talk about what the curve is based on and also its limitations, and also some changes that are coming in the Ecometer software and how you can modify the way that it's using this curve to calculate the gas rate and essentially the percent of liquid here in the annulus. Then continuing in section 3, this is still in overtime here. We're going to look at producing and static bottom hole pressures. So producing bottom hole pressures, we've kind of already talked about that with the S-curve, but we'll get familiar with how that's computed. And then we'll look at static bottom hole pressures. If you have a well that you turn off or it goes down due to a failure, the fluid level is going to rise up to a certain extent until the point where the pressure exerted by the casing pressure in all of these columns of fluid is equal to the pressure of the fluid way out there in the reservoir. So this is what we would call our static bottom hole pressure. If we can calculate the pressure down here on the bottommost perforation, we then understand what is the pressure of the fluid out here deep in the rock. And we can use that to understand just kind of where is the reservoir in its life, but we can also tie that in with what's known as inflow performance relationships. So an inflow performance relationship, this will be the next topic. It's a relationship of the producing bottom hole pressure in relation to your static bottom hole pressure. So the relation of that tied in with what your production rate is. And we'll look at two different models, the Vogel curve and the productivity index. You can see they have a different slope and they're going to calculate different values. But most people, when they do fluid level shots, are not going this far, but this can be very valuable if you want to, let's say, make a prediction on the production rate. Let's say if you have a rod pumping well and you cannot pump the well off and you're pumping it as fast as you can, and you're thinking maybe we need an ESP on this well, or maybe we need a bigger pumping unit and we need to upsize everything. Well, that's going to have a certain cost to it. And then the question is well, what are the economics? What's the payout going to be? So what is my increase in the production rate going to be if I can get my bottom hole pressure lower than what it currently is? Well, that's what you can use inflow performance relationships to try and understand. So we'll talk about the theory of this and how you can apply essentially the relationship of your pressures, producing versus static, in relation to an existing production rate for a particular well. And then we'll go into shooting different forms of artificial lift systems. So for the most part on this course, you're going to see rod pumping related images because it comes from my rod pumping diagnosis and optimization course. Now in that course, I also talk about other forms of artificial lift scattered throughout the course. But in this section right here, I'm focusing specifically on the other forms of artificial lift and trying to give you some tips and tricks when you're dealing with those. So for example, if you have a gas lift well, it's quite common where the gas lift mandrels will send reflection back, and you can use those as downhole markers to calculate the acoustic velocity. Or if you're working with progressive cavity pumps, they tend to make a lot of noise, background noise at the wellhead when you have that top drive that's rotating around. It's shaking the tubing in the wellhead, and you tend to get lots of background noise. So I'm going to go through some different examples on different forms of artificial lift and just things that I've learned in this particular section. So that finishes off section 3. And then we have the final quiz, which is 2 hours, and you should not skip this. There's going to be a question related to every important topic that we discussed in the prior sections, so highly recommend that. And then also, as I mentioned, there's the Echometer equipment and software section, which you can take if you're interested, and you can take that in any order you want. If you do want to take it, I would probably wedge it in right here before you go on to the next section. So there is a detailed course outline that comes with this course, and if you will scroll below this video right now with your mouse, as you're watching me, just scroll down. You're going to see all the attachments for this course. Go ahead and download those, save those in a folder. But in the outline here, it shows you what topic we're going to hit in what order, and it also shows you the video number. So for example, if you want to look at the 3 methods for calculating the acoustic velocity and you want to jump to there first, notice that starts here at the end of video 2.3, and then it picks back up in video 2.4. So you can use this to understand where we're going in the course. And let me also say, as I mentioned, this course has been lifted out of my larger class. And so when you look at the, for example, fluid level shots part 1, when you go to this video in the next section, it's going to show up like this, section 4. Fluid level surveys. Well, that's the wrong section number. Don't worry about that. That's just because I pulled this out of my larger class and I did not change that first slide. Don't let it confuse you. Now, let me tell you a little bit, a few recommended references, and then I'm going to do a high-level overview of fluid level shots and also dynamometer test quickly, because you will hear about dynamometer test or dynamometer cards in this course, and I want you to understand that, and that's what we're going to finish off this section with. And now let me tell you a few recommended references quickly, and this is something you're going to see throughout the course. And so there's lots of papers that are referenced throughout the course if you want to look them up, and most of them are going to have this abbreviation at the end of the paper, the Southwestern Petroleum Short Course. So this is an oil conference that goes on every year in Lubbock, Texas, which is just a couple hours north of Midland, and it usually occurs in April. And I'd highly recommend it if you're interested. But it's a 2-day conference, and there's usually about 8 different rooms where papers are being presented all at the same time. So you can pick which papers you're interested in and go sit in on those papers. And there's lots of papers related to artificial lift systems or rod pumping systems, which I'm most interested in myself. But the great thing about this reference right here is that if you reach out to them, you can buy the full catalog of papers for about $300. And it's all the presentations that have been presented at the short course going back to 1954. And so you can take all those papers, they're broken down by year, and you can do keyword searches on them to try and find specific topics. So if you're interested in co-rod or asphaltenes or specialty types of pumps, you can find lots of papers that reference it. That's why you're going to see it so frequently. Now, I also reference a lot of Echometer papers. Usually when I do, it's going to have this abbreviation at the end because that's just how I found the paper, by looking it up through the different folders from the short course. But all of Echometer's papers can be found for free on their website if you go right here. And they have the best papers related to fluid level shots, as you can imagine, because they created the fluid level gun. So you can learn a lot just by reading Echometer papers. I highly recommend that. Now, I also have my short course. This is what I call the sucker rod pumping short course, and I got the name here from the Southwestern Petroleum Short Course. This is a 6-page rod pumping brochure. It does have some information related to fluid level shots. There's also there's going to be some valuable information in there. It's not as important for this particular course because it's more focused on rod pumping systems and dynamometer related testing or downhole gas separation, that sort of thing. But this is going to be a helpful reference that I would recommend. So this is also going to be in the handouts when you scroll down below this video. And so if you see this pop up in the course, that means on my sucker rod pumping short course, you can find the information I'm talking about on a specific page. That way you don't have to write it down in your notes. You can just go highlight it. Now, my favorite book in the industry, this is a rod pumping book. Again, it does have some information on fluid level shots. This is by Bomber and Podio. This is the Beam Lift Handbook. But if you're interested in rod pumping systems, and a lot of fluid level shots are taken on rod pumping systems, this is a great book to have. So it goes into everything related to rod pumping with beautiful images and pictures and graphs. And it's just, it's very visually aesthetic and pleasing to the eyes. Now, my second favorite book is also by Dr. Podio, who was a longtime consultant for Echometer. And this book right here was written with Jim McCoy, who is the founder of Echometer. And this is Acoustic Fluid Level Measurements in Oil and Gas Wells Handbook. This is specifically and only on fluid level shots, and I highly recommend that book if you want to get really good at fluid level shots. There's lots of great theory. We're going to talk about it in this class, and there's also lots of interesting examples, but these are my two favorite books in the industry. Now, when it comes to abbreviations, you're going to see a lot of abbreviations in my rod pumping brochure, and you might see some sentences like this in the rod pumping brochure or on the slides. At the end of this brochure, on the last page, there is a list of abbreviations that you can use. As we go through this course, I used to have a list of abbreviations. I don't think you need it though, because as we go through the course, I will try to read out each abbreviations. I would read this as the traveling valve is attached to the plunger, and on the downstroke, the pump intake pressure is compressed to the pump discharge pressure. So I use the abbreviations just to try and keep the slides with as minimal of writing as possible, because it gets boring if you have too much writing all over slides. There are some example files for TAM. This is Total Asset Management. This is the Echometer software that you're going to use if you're using the wireless equipment from Echometer. It is a free software that you can download from their website, but there are some example files that we will look at together as a class. So for example, this might pop up on a slide. Here is the name of the well file that you can look up. And if you import it and you do not change the folder that it imports into, this is going to be the default folder it will import into in your TAM software. It's going to be eCourse examples. And some of the examples that are included in this course were recorded with version 1.8.56. Many of them were recorded with an older version of the software. But if you're trying to open up some of the examples and they won't open, it's probably because you have a version of the software that was before this. Now, as I'm recording right now, at the end of 2024, TAM 1.9 is out. So if you have version 1.9 or anything later than that, you should be fine to open up these example files right here. If you don't know what version of the software you have, if you open up TAM and click Utilities, a box pops out and you click About. That will tell you what version of the software you have. And if you don't have the latest, I recommend you get it. They're always improving it, and you can find it at Echometer's website if you look up the TAM software. Now let's quickly do an overview, a high-level overview on both fluid level shots and then also on the fluid level gun and the dynamometer system. So think about this. Why would you want to take a fluid level shot on a well? Like, what is the purpose of it? Sometimes you have some cool technology or something, and I've had people give me these sort of things. They're like, hey, check this out. And it's like, okay, that's kind of cool, but like, what do I use it for? What is the value of it? And that's what I'm asking right here. What is the value of a fluid level shot? Why do we want to take fluid level shots? Well, the main reason that you usually take a fluid level shot is you want to understand, is the well making all of the potential production? So are we getting all the fluid out that's above the pump intake? And you can only produce things that are at the pump intake or above. You know, your pump can't have a little straw going down to the bottom well, sucking it up. So we're looking to see how much fluid is above our pump intake, depending on whatever form of artificial lift we have. If we have a rod pumping system, where's our seating nipple set at? That's what we want to know. How much fluid is above our seating nipple? So are we making all the potential production? Is our well pumped off? Is how we would normally say that. And if it's not pumped off, how much liquid is above the pump? And what is the producing bottom hole pressure? So if you're not getting all the potential production out of the well, how much is still down there, and how much back pressure is that creating on our producing formation? And we all understand the fact that you want to get the fluid level low, right? We want to get the liquids out of the well. We want to get them in the tanks and sell them. That's our revenue. But the lower the fluid level is, and the lower the bottom hole pressure, the greater the reservoir drawdown. So you have the pressure of the fluids out here in the rock, and what's pushing the fluids to the well is the pressure difference. That's what's causing the fluids to come out from the reservoir rock and come through the rock over to your well. And the lower the bottom hole pressure, the more production you're going to make. So if we're not getting all the production, how much do we still have down there, and how much back pressure is that creating on the formation? Another reason for a fluid level shot is to try and understand what is the reservoir pressure. So we talked about the static bottom hole pressure. That represents what the reservoir pressure is, and that's a way that you can kind of track your reservoir. Or maybe you have a water flood that you're just instating in a field, and you want to see where's that water going? Is that water distributing around through this whole reservoir, or do you have pockets where the reservoir pressure is higher and other places where it's lower and that water's not getting to? You can use the reservoir pressure also for the inflow performance calculations that we're going to talk about. Now, another great reason for fluid level shots is going to be troubleshooting. So if your well is not pumping, the question is why not? If it's not pumping due to a failure, one of the first things I will do is I will hook the fluid level gun up to the tubing, and I will take a fluid level shot down the tubing. Now, if you have a form of artificial lift that has a standing valve in the bottom of the tubing, your tubing should be pretty much full of fluid. I should be able to find that fluid level at surface or very near surface. But if you find the fluid levels somewhere 4,000 feet down in your tubing, well, that probably indicates that you have a tubing leak is the most likely cause. Of course, it could have drained or something else, but this is a great way to troubleshoot problems. Or maybe the well's not pumping. You might take a fluid level shot down the backside and find that there's no liquid in the well, and that's why it's not pumping. So you can use fluid level shots for troubleshooting wells when they're not acting the way that you expect. You can also use them for troubleshooting when it comes to ineffective chemical treatment. So maybe if your chemical treatment is not working as planned, you should take a fluid level shot down the backside. Most of the time when we introduce chemical into a well, we have a pump truck that drives up to location and he dumps a bunch of chemical down the backside. Or you have a tank on location that's continuously pumping chemical that's just dropping in at the wellhead. And that chemical is supposed to drop all the way down and then get sucked up by the pump and go to the inside to protect the inside of the tubing and maybe a rod string if it's a rod pumping well. But if your chemical is not working effectively, maybe you should look down the annulus, because that's where we're introducing the chemical. And what you might find, and I've seen this many times, let's say you have continuous chemical treatment, chemical is being injected right here at the wellhead, and it's supposed to come all the way down to the pump intake, but the top of the fluid level is at surface. And there's so much pressure down here and so much gas that's coming up the annulus that the well is flowing up the backside to some degree. So any chemical that gets introduced into the casing, just whoop, it gets pushed up and out and down the flow line. That chemical is not getting down hole. Or you might find that you have a huge pad of fluid here on the backside, and maybe you need more flush volume when it comes to your truck treating, or to the you need some more fluid from your slipstream to help carry that chemical down through the large pad of fluid. So it can be helpful when it comes to troubleshooting ineffective chemical treatment as well. Now, another reason to do a fluid level shot is just to get a baseline. It's just like kind of going to a doctor and just getting a checkup, maybe go to the doctor every 5 years and say, do some blood work. How do I look? Well, a fluid level shot is going to pick up any anomalies or large kicks in the annulus that you might want to investigate, or at least know that they exist. Here's an example of that. So here is a fluid level shot. This is the acoustic trace. There is a big, massive casing leak right here, a huge upkick. Now here is the top of the perforations. That's an upkick as well. And here's the fluid level kick. Now you can't see these very well because I'm zoomed out, focused in on the casing leak. If you zoom in, these become more clear, but this casing leak right here is massive. So that would indicate maybe even the casing is parted right there. And if not, you have a massive hole in the casing. Now that doesn't mean that fluid is actively coming out there, but you might have a cavern that, or you might have a casing leak, and behind that casing leak is a cavern, and it might have been squeezed off with cement. And that's exactly what this is right here. This is a well that a customer acquired several years back. The first fluid level shot on it, I'm seeing this huge kick, and I reached out to the engineer and it was asking, do you have a perforation right here? He's like, no, we don't have a perforation. Well, it's like there is a huge, massive hole in your casing. Doesn't mean that any fluid's coming in from it. And usually if you have a big active casing leak, you can't see it because the fluid level will be higher above that casing leak and you can't see below the top of the fluid level. But you can get a baseline on a well and you can see this sort of thing. I found many wells where the casing actually parted higher up near surface. The company had no idea, but I picked it up with a cheap, dumb fluid level shot. So for all these reasons, this is why you would want want to consider taking a fluid level shot. Most of the time, though, we just want to know, are we getting all of our potential production for the given circumstances? So there are two diagnostic tools that I primarily use at Downhole Diagnostic, and we're going to be focused on the first, that is the fluid level gun. So the fluid level gun, we hook up to the annulus and we're looking down the annulus. We'll see the top of the fluid level, but we'll also be able to interpret what the bottom hole pressures are. And on a high level here, the fluid level gun tells us how efficiently is the well producing the reservoir. Okay, so we have a certain amount of fluid that's coming in, and we want to know, are we efficiently producing the reservoir? Are we getting all the fluid that's coming out? So another way of saying this is the liquid producing efficiency. So are we getting all the liquid out that is residing above our pump intake? Now, it doesn't exactly tell you how efficiently you're producing the reservoir in one regard, because of course you can have scale on your perforations, you can have some near wellbore damage, maybe your seating nipple is set too high and it should be down lower. So for all those given reasons, it doesn't tell you fully how efficiently you're producing the reservoir, but for the given circumstances. So for the given depth of where the pump is set, for the given condition of the perforations and, the near wellbore region and whatever your frac wings look like, for those given conditions and the amount of fluid that's coming in, are we getting all that fluid out? If we have a well pumped off, that means our liquid producing efficiency is high. Let's say 100%, assuming we have low casing pressure, which you should have on most forms of artificial lift, or at least rod pump and ESP. So another diagnostic tool that we are not going to really talk about, but you will see references to this throughout the course. I also have other courses on dynamometer testing. A dynamometer, this is a measurement of load versus position. So this is the load right here versus the position of the stroke length. We're measuring at surface. So on the top rod, on our polish rod, this is the surface card right here, and it's a measurement of the load versus position on the polish rod or the pumping unit as it's stroking around. And then you can calculate what's happening downhole at the pump plunger. How is the pump picking up and carrying the fluid load, and then how is it releasing the fluid load, and then the plunger moves back to the bottom of the stroke. So this rounding right here indicates something. This delayed release in the fluid load indicates something right here. So this is a dynamometer test. It's looking down the rod string as to what's happening downhole at the pump. And so the dynamometer tells us how efficiently is the system operating, or another way of saying that is the mechanical producing efficiency. So let's look at a scenario. So let's say you have a well that's pumped off, right? And you're getting all your production. Liquid producing efficiency is 100%, but maybe that well's running 100% of the day and it's only got 50% pump fillage. So how efficiently are we producing the well mechanically? Well, we're not. We're only filling the pump with 50% of fluid. We should give that well some downtime and try to maintain 100% pump fillage. So both of these tools, what's magical about these for a rod pumping well, because a dynamometer is only applicable to a rod pumping well, but you're looking down two different sides of the well. This one's looking down the annulus to see how much fluid is above the pump and what is the pressure of that fluid going into the pump. This one is looking down the rod string as to what's happening down there. How is the fluid load picked up, carried, and released? And that's based on the downhole card. And we can interpret by looking down both sides a very complete picture as to what's happening downhole in something much more sufficient or better than just standing around looking at a pressure gauge. So if we look at fluid level shots, this is the three scenarios you're going to typically find. Okay, so you have a fluid level at surface, and you have no gas producing up the backside. That's not a normal situation for a producing well. You'll typically, in some places, if you have high bottom hole pressure, you'll find that on inactive wells. But I have seen that on producing wells in water floods, where they have a rod pumping system that's making 200 barrels a day, but that reservoir will give so much more fluid than that pumping system could ever handle. The fluid level essentially sits here at surface. But what is the liquid producing efficiency in that case? Well, it's almost effectively zero. Like, you're not getting nearly as much fluid, and you might not want all the fluid that you could get in a water flood situation if you're getting that much fluid from the reservoir there. But in that case, you have a very high bottom hole pressure, and so your liquid producing efficiency is zero. If you jump over a pumped off well, 100% liquid producing efficiency, or you have something in the middle. The fluid level is not at surface, it's not at the pump intake, and it could be anywhere in between. And then the question is okay, how much liquid is residing above that pump? Remember, this is our gassy fluid column, but we want to know what percent of that is gas and what percent of that is liquid and what the bottom hole pressures are. So again, liquid producing efficiency. Now, dynamometer test measures the mechanical producing efficiency. And if you don't know anything about dynamometers, remember this is the ideal card. card. It is a rectangle, and it represents this. The plunger rapidly picks up the fluid load. It carries the fluid load to the top of the stroke. As the plunger transitions into the downstroke, it rapidly releases the fluid load, and then the plunger moves back to the bottom of the stroke. So this is the ideal card, and that represents 100% mechanical producing efficiency. All these other cards here represent some degree of inefficiency. So this represents the lack of liquid to fill the pump chamber. That's what we call fluid pound. The fluid load is released in a sudden and delayed fashion. This represents the fact that there's free gas getting into the pump. This is what we call gas interference. So there is enough liquid to fill the pump barrel, but we have free gas getting in. We need to reevaluate our downhole gas separator. Here we have lots of slippage, which represents that we likely have a very worn pump. Here is a hole in the pump barrel for a bottom hole down pump. You can see the fluid load picked up and carried, but it's released well before the top of the stroke, which is right here. So all of this is lost efficiency. And this is the ideal card, except that it has a mechanical tag. And so we're beating our equipment up. And so we don't have complete efficiency in that regard because we're damaging our equipment. Now, other things you can see with dynamometer test is something like this. Another degree of looking at the efficiency is how effectively are you getting the surface stroke length to transmit motion to the downhole plunger. What contributes to production in a rod pumping system is the movement of the plunger relative to the barrel. So here we have a well that's got 120-inch surface stroke length, but the downhole stroke length on this shutdown card when it was pounding fluid is only 25 inches, which is terrible. And some people said, well, it looks like the plunger might even be stuck there. It wasn't stuck. This is what the cards look like when the well was pumping, when it had 100% fillage. But even in this case, it's only about 40 inches of downhole stroke length. So there's a huge degree of inefficiency in this system because we have a stroke length that's much longer than what we're transmitting to the downhole movement of the plunger. And what's the reason for that? Well, this was a deeper well, about 11,000 feet. It had about 8,000 feet of 1-inch fiberglass rods. So that's a lot of fiberglass rods. It's also the smaller diameter of fiberglass rods. And it had an 1.5-inch pump. And also the surface stroke length is pretty short for that sort of depth at 11,000 feet. And the unit wasn't running fast. It was running very slow, so we weren't getting over travel. So for all these reasons, it's just kind of a bad design overall, but it represents inefficiency in the system, just like the dynamometer cards do. So when you have a rod pumping system, you can take a fluid level shot on the well, but it only kind of gives you half of the picture, and it's really valuable to have a dynamometer card to go with it. So for example, you might have a well, let's say you take a fluid level shot, and this is what it looks like. Okay, so we have a decent amount of fluid above our pump intake. That's what the fluid level shot shows, but it doesn't tell us why. Okay, so we have a lot of fluid above the pump, but what is the reason why? Maybe we don't have enough capacity to our system. We need to increase the strokes per minute. We need a bigger downhole pump. We need a longer stroke length at surface. Or maybe we have enough capacity to produce all the fluid that's coming into the well, but we have some degree of inefficiency. Maybe you have a worn pump, or maybe you have free gas getting into the pump, and your pump fillage is about 50%. So it takes twice as many strokes to get the same production. So you can't see the complete picture with just a fluid level shot. It's like half of the information, and that's why you always want to combine it, if it's a rod pumping system, with the other half of the information, which is a dynamometer test. So very quickly, I'm going to show you the steps. This is kind of a one-page summary of the course, or the most important information, putting everything together. So if you want to take a fluid level shot, what you do is you take your fluid level gun. Here is the pressure chamber. We'll pressure that up, let's say to 800 psi. We're going to then connect it to our well. We're going to open the valve, and now we have pressure communication between the gun and the well. And remember, there's a microphone right here in the bottom of this gun that's recording the sound waves. After we connect it, we're going to close off the valve to the flow line. So any gas coming up the annulus is now trapped. And then we take the fluid level shot. And one of the main reasons to close that valve to the flow line is it's going to minimize the amount of noise that's being generated by the gas flowing up, but it's also important to do that for the casing pressure buildup test. But after we close that off, we take the shot, and the sound waves that are reflected back to the microphone are recorded on the acoustic trace. Here's another acoustic trace. This one is quite interesting in itself. It's got all sorts of kicks going on due to the different perforation intervals that wave is encountering. And then here is our fluid level kick on bottom, which is right here around the intake for this particular tubing design. So this is our acoustic trace. Now, in order to calculate the depth to the fluid level, you first have to identify which of these kicks is the fluid level kick. We'll talk about that in this course. How do you identify that? And then secondly, you need to know how fast is the acoustic velocity, or how fast is that pressure wave traveling? What is the acoustic velocity for that particular well? We need to calibrate it to something because the acoustic velocity changes based on the composition of the gas and the pressure and the temperature of the gas. And the normal variation is usually between 800 to 1300 feet per second, which is a huge variation. So it's very important to have a good estimate of how fast that pressure wave is traveling. So once we identify the fluid level kick and we properly compute the acoustic velocity, after that you do the casing pressure buildup test. So let's say we have the top of the fluid level here. You see how fast the casing pressure rises. That then feeds into our correlation. Then we have our output here, which is the model of the well. This is what we call the G-flap. This is the gas-free liquids above the pump. So you might have a gaseous fluid column that let's say this is, I don't know, 3,000 feet high. But then your gas-free liquid above the pump, maybe that's only half of it. Maybe it's only 1,500 feet high because half of this was liquid and half of it was gas. And then based on this, we can compute our pump intake pressure. What's the pressure of the fluid that's going into the pump? And we can also compute what our producing bottom hole pressure is. And then if you want to get fancy with it, and if you have a well that's not pumped off and you want to understand what is the maximum potential production I could get from this well, you can do some modeling like our inflow performance relationship. So this is all the information that we're going to go through. And of course, we're going to go into a lot more detail with a lot of segues along with it to try and make sure that we become experts on fluid level shots in this course. So to finish it off, let me leave you with some Soviet propaganda because my wife is Russian. She was born in the Soviet Union. She is a tough cookie. But skori vi ponedelnik I snova na robotu, which means I can't wait for Monday to come so I can go to work. And I hope that is the feeling that you have right now, my friend, as we're about to jump into the course. And remember, as you start the next section, it has the wrong section numbers. Don't let that confuse you.